All right, so we're going to talk a little bit today about levels of representation. So this is levels of representation. Specifically of matter. So we're going to kind of go through the same type of we'll just look at water, for example, in different phases and show how different symbols can mean different things. So, for example, let's start with the macroscopic view or representation for the three different phases of water. So we can have water as ice, a liquid, and as a gas. And so we're going to represent these. The macroscopic representation would just be how we would think about it for every day. So this is a cube of ice. Liquid, we could think of it in a container, so like a beaker. Or we could think of as a gas, we have in a balloon. Or we could think about it, technically, we might not think about. We could have it in a container with a lid on it. Maybe it's a piston where we have hydrogen. Well, we can't, actually, I'm going to remove those little dots because we can't really see it. Balloon is a good way to visualize a gas that we might be able to see. In this case, it would be water vapor. So these are very concrete ways in which we think about water and its phases. And so the macroscopic view of the world is actually one which is concrete, which means it is something that we are very used to, something that is not new to us. It doesn't need much translation. It doesn't provide us much in the way of information of why things do the things they do. It does kind of give us an idea of what. We know that a solid, so in this case ice, maintains its own shape without need of a container. We can see a liquid takes the shape of a container, where a gas expands to fill the entire container, in this case a balloon or a piston, where a liquid does not. So there's different differences that we can see, but that's about it. So the symbolic way in which we can represent these three phases of water is going to be quicker to write. This is going to be, I'm going to say, well, this is, well, if they're all water, and all I'm going to do is I'm going to change the subscript. So if it's ice, it's a solid, so I'm going to put a S. If water is a liquid, I'm going to put an L. And if water is a gas, I'm going to put a G. So very simple. That took a lot less time to draw because it was this basically just a symbol. So we in chemistry tend to use a symbolic representation a lot, especially in reactions. In the notes so far, I've used it a lot. The main downfall about symbolic representation is it requires translation. You, as a reader, need to know that this means solid, that this means liquid, and that this means gas. We also need to know that H2O is a way to write the formula for water. So lots of translation needs to happen here, and so this can actually lead to not being very clear. And again, we can do things. I'm just going to put this in here and I'm going to erase it, but just to show you, you might see when we'll be drawing structures like this, where we have, this type of structure, and you might not know what exactly that represents. This is a different representation where these are actually carbons, and there's actually hydrogens not being shown. Carbon here. These are just a quicker way to write it. And so again, we're going to go over this, but this is just to show you how you need to be able to translate these kind of short form symbols into their actual meaning. And the last way of doing this is the microscopic. So microscopic, give yourself a little bit of room here, like I've done. So microscopic, if we look at the solid H2O, what we're going to see, I'm going to draw one of these circles as a water molecule. So a water molecule in the solid form takes up a very organized and unique structure. And within that, it is bound together very tightly by bonds. So we can see these interactions happening within water, and so these are hydrogen bonds. They're interactions. They're not formal bonds, but they are strong interactions that keep these water molecules from moving too much. So that's the solid water. If we look at liquid water, we're going to have, it's going to be in a container, but we're going to have water molecules that are going to be interacting, maybe have just broken interaction. They are generally, these might be interacting. We might have a water molecule off by itself, which might have been going this way towards this one. So there's still interactions, but there is movement, fluidity within the hydrogen molecules in the liquid that allows them to go and change interactions between different molecules. Where if we look in the here, these molecules are locked, so they're not going to be able to move around. It's kind of like they're all holding hands and they can never let go. Where these are kind of like dancing partners, and if you think about it, that they can switch who they're holding hands with throughout the course of a song, so to speak. If we were to extend that metaphor, probably longer than it needed to be extended. And the last is gas. So gas molecules, water, we're going to see them going woo, going. They are moving. They're flying by. We might actually have them kind of having collisions. So there is lots of motion happening within the gas molecules. They are not assuming to have any interactions at all. And so this explains a lot of their properties. And so the microscopic representation of atoms and molecules and interactions are very useful for explaining things. And in such a way that that you can't get from the other forms of representation, symbolic, or from the macroscopic. And so there's the downfall, as you saw, is it takes a lot of time to draw the microscopic representation, and it's all a cartoon. These are not actually, these are representations that we are making. It's not true. It's not real. So there's always some limitation to how we can represent something in the microscopic world that lacks accuracy, lacks the detail that's actually there. And so, there's some downfalls there, but it does provide us the most comprehensive bits of information that we need to kind of understand the whys, the how things are working. And so, just one more example that we can do, we'll use this representation triangle at looking at a salt dissolving. So we'll do the macroscopic. We will have the microscopic. And we will have the symbolic. And we'll do this in the same way. We'll start off with the macroscopic, and we'll say, okay, we have salt. We'll put this in water. We have a salt. Let's say just a chunk of solid, so NaCl, solid. Again, I'm using symbols here, but this is okay. So we're going to put this in, and we're going to see that the NaCl goes away. So what changes? Well, maybe we put in a thermometer, and we see that the temperature increases. So we see an increase in temperature. The temperature of the mercury is rising, or colored alcohol nowadays. And so we can say, well, there was a change, even though the NaCl seemed to disappear. We can measure, we can see that the beaker got warmer. The water in the beaker got warmer. We can measure that with the thermometer. Something definitely happened. We don't know what. We don't know why. Okay. And so we can connect this to the symbolic. We can say, okay, well, we know something. We can represent this a little bit quicker. It doesn't really, this is not going to get to the why. But we can say we have NaCl solid plus pure water, liquid, goes to form, I ran out of room here, so I'm going to have to put on the bottom, goes to NaCl. And now we're going to use a news term, it's AQ. This stands for aqueous. Let me rewrite that because that was written pretty poorly. Sorry about that. And aqueous is basically something, a solid that is dissolved into water. Okay, so it's AQ. And so this is our symbolic representation. Again, it's showing us that, okay, so what we can tell that's different here is that we can say we go from NaCl solid to NaCl aqueous. So we know that NaCl is still there, but based on this symbolic representation, it kind of looks like Na and Cl are still bonded together, which is not the case at all. And so we have to go to the macroscopic view to really link these, sorry, go back to here, link these two together. So if we want to link all three, the microscopic is really going to do that. Sorry, I said microscopic. And so we can see what's happening here is that when we start off with NaCl solid, so NaCl solid, what does that look like? Well, it looks like it's a big cube. And if we were to zoom in, we could see that we have Na plus surrounded by Cl minus. And that we have NaCl, Cl. That these go around in a matrix of alternating Na, a positive and negative ions, and it goes on forever. It's an ionic matrix. And that when you put that, and that water looks like water molecules, like we already drew, kind of have this structured network of bonds where they're bonded out in a very systematic way. So this would be H2O liquid. And when you add these two together, you get specifically a water molecule is a oxygen bonded to two hydrogens. And it turns out that the oxygen likes electrons a little bit more than the hydrogens. And so it has this little lowercase delta is called, we use this as slightly. It's not a full positive charge, but it's slightly negative. That's what delta stands for. And this would be slightly positive. And so what happens is positive and negative charges interact, or attract, sorry. So we have the oxygen from the water pointing itself towards that positive sodium. And we'll do a little circle around here to kind of see that sodium. So we have I'll do the interaction, different colors, maybe in red, that we have this water kind of interacting in a unique way. And we also have the water still interacting with itself. So if I draw this out, the water can interact with itself. And we have the Cl minus surrounded by the slightly positive hydrogens. So this is taking a while to draw. You can see, but it's really providing us a clearer picture. So what's happening, what's the difference? If we go back to here and we say, what is the difference between NaCl solid and NaCl aqueous? Well, it's this. It's the fact that these are not, so the Na and the Cl are no longer bonded together. So they are separated by the water. And that water is replacing those ionic interactions with its own polar interactions. Again, we're not going to get into all the details, but I'm going to point out we can see in the microscopic view that NaCl solid looks different than NaCl aqueous, and the aqueous really telling us that the Na and the Cl have broken apart. They are no longer interacting with each other, but they are interacting with the water instead. And so this, again, is a really good example of how the microscopic tells us the why, what's different. And then we can also see and help explain why the temperature has gone up, because we have broken bonds between the Na plus and the Cl minus ions, and we've created new bonds between the water molecules and Na plus. And in doing so, we have released thermal energy, which increases the temperature of the water. So we have an understanding of why. So again, the point I'm trying to make is that to really communicate this, to understand it, you need all three levels of representation. You need to be able to see what a salt looks like. In your head, you can visualize, this is concrete. This is something we can do in the real world. We need to be able to write this quickly, and you need to be able to translate what's going on. But to be able to translate, you really have to understand what's going on at the microscopic level, at the molecular level, and we have to be able to represent that in some way. And so microscopic representations are useful for that. And so we're going to be using PhET sims a lot in this class to help build those microscopic models in our head and interact with those in a way that's realistic and accurate, to help us understand kind of these shorter symbolic representations. Okay, hopefully that was helpful.